Hello.
Yes, sir, you are audible.
Okay, thank you. So, should I start now or wait few minutes?
Sir, let us
Sir,
just give 2 minutes, 2, 3 minutes, let other participants join and then we'll start. Presently, Dr. Shah is working as Associate Professor in Department of Computer Science Engineering at J.K. Lakshmipat University. His areas of interest include artificial intelligence, deep learning, smart world algorithms, and network science. He holds 15 years of development and research experience in the areas of data and information science, covering information retrieval, web mining, decision theory, social network analysis, and big data technologies. Dr. Shah started his research career in the field of web mining as a senior research scientist in the Center for Soft Computing Research, a national facility, Indian Statistical Institute, Kolkata, where he worked for a duration of 5 years. Some of his notable contributions during this period includes the development of ensemble classifier based on rough sets, among many others. He has co-authored a book titled Advanced Data Structure, published in CRC Press, in addition to 25 publications in internationally reputed journals and conferences. Sir, we are glad that you have joined with us, and I would now request you to please continue with the session. Sir, your mic is, it seems, mute.
Good afternoon, all of you. Thank you, Amrita, for introducing me. So, uh, you have learned a lot of things, and this is probably the last session of this workshop. And we will learn most fascinating area of artificial intelligence called reinforcement learning. So, at the beginning, I have a question to all of you. Have you seen that movie called AlphaGo, which is award-winning movie from Deep Mind Lab by Google? So it's probably if you have not seen that, so let's start from that point. I want to share, and that is a big movie. We cannot. Okay, so is my screen visible?
Yes, sir, it's visible.
So let's play
Very
this.
good. It's missing the ball most
Is
of the
this
time,
audio
but
visible?
it's starting to get the hang of the
Yes,
idea
audio is
that the bat should go
audible.
towards the ball. Now, after 300 games, it's about as good as any human can play this, and pretty much gets the ball back every time.
Okay, so
Welcome you all to Etsarthi.
oh,
For your mains examination preparation, टेस्ट सीरीज की इम्पोर्टेंस वी ऑल नो एंड रिसेंटली जिस टाइप के वीडियोस काफी लोगों ने डिस्कस
okay, so what is this movie about? This is basically this AlphaGo movie is basically this is the Go board, okay, where people play Go. Hmm. This is black and white
It's
boxes.
intensely contemplative.
This is black and white boxes, and the target is to cover maximum area. Any two player can play, and their target is to cover maximum area. Who will win? Okay, so this is the Go game. It is more difficult than chess, and it was solved using reinforcement learning. So and it beat the most best human player in 2007, Lee Sedol. Okay, that was the achievement of the AI of that time. Okay, so I am showing you one more. Let's stop share this. Okay, here is one more thing. Here is one more thing. This is about autonomous drone. Okay, it was an initiative by Stanford University.
This program is brought to you by Stanford University. Please visit us at stanford.edu.
So what you're seeing today is by far the most difficult aerobatic maneuvers flown by any computer-controlled helicopter.
The goal is always for us to take really hard problems that humans are very good at solving. For instance, Garrett can pick up any helicopter, even ones he's never seen, and go fly amazing aerobatics. So the question for us is always, why can't computers do things like this? So our goal is to build software that can learn to go fly a helicopter the way that a human being can, and that way we don't need so much engineering effort to build control systems like this.
So the basic technology used to develop
Okay, so what they are doing actually, that is a autonomous helicopter, and they are it is humanless. There is some reinforcement learning agent. The program is working and it is trying to learn. So now let's come to our lecture. What we will do? Okay, so we will basically so here is the program which we will cover today. We cannot train that helicopter at this moment, but at the starting point, this is a program. This program is for tic-tac-toe. Okay, this is a very small program written to solve the tic-tac-toe, and after several training, we got this board position. So these board position are, we all know how to play tic-tac-toe. I have assigned this QWE, this board position as QWE, and then ASD, and then ZXC. So if I play the game, let's say I am starting with S. So the agent is playing X. I am playing star. Okay, and agent is playing X. Okay, so this program you will also write this program. So it is playing X. So what will be the next move? I can play anything. Let's say I can play C. Okay, so agent is playing. I have trained this program very high, so it is very difficult to beat this program. So let's check. Uh, let's stop the winning condition of the agent. So I have to put W. Okay. So it is going to be a tie. Okay. Nobody can win because agent is very much 10. Okay. So let's say I am putting A here, and this is basically a tie. All the position are filled except the one box, and if we select this box, it is going to be tie. So let's put Z, and it is a tie. Okay, and new board is given. So this is the program. Now how agent is trained, we have to learn that thing. Okay, so let's come to the theory, how it is working. Okay. The slide is visible to all.
Yes, sir, the slide is visible.
Okay, so let's go for full screen. Okay, so today we will learn reinforcement learning, which is a part of machine learning or artificial intelligence. So it is different than deep learning and than neural network setting. It is totally different. It is all about how a small child learn the thing. Okay, he don't have any idea about the environment. We don't need much idea about the environment, but we make some action and environment give us some reaction. Okay, from that point we learn the things. So here are some example of control learning. Okay, so some example like robot is learning to dock into a battery charger point. Okay, or learning to choose some action to optimize some factory output. Okay, or learning to play some game, any game. Okay, these are the example where we can apply reinforcement learning. Okay, it can be applied in self-drive car also. Okay. So how it is done actually, uh, let's come to this picture. Okay, there is an agent. What is the agent? Agent is a program. Okay, this program is in some state, like some driver is sitting in some car, so it is in some state. Let's say the car is standstill, it is not moving, so that is a state. Now car is starting to move forward, that is a state. It has the other option, it can move left. Okay, that is a different state. It can move right, that is a different state. Okay, so these are different state. So agent has to choose some action. So here is an agent and the environment will give some reaction. Okay, so what is the action? Agent can took any action and it will be played on the environment. Okay, in response the environment will change the state of the agent. Okay, change the state of the agent, and correspondingly agent will get some reward. Okay, this reward is very important thing. Okay, for example, if I choose that tic-tac-toe example, a win means a reward. Okay, and a lose means a negative reward. Okay, we can treat in this way. So every time some agent is playing some option, if it is winning, it will get some positive reward. It is losing, it will get some negative reward. Okay, so there are so many state, and every time the agent is performing some action. So it is a time series thing. We are in state 1. Let's say S0 is the starting state. Okay, and agent is performing some actions A0. Okay, so agent will, and so the system will reach to the state S1. In S1, agent is performing some another action, so system will reach to the state S2. In this way, there will be a long sequence, and there is a reward associated with the every action. The reward is basically, it is in the different direction. Reward is given from S1 to S0, S2 to S1 in this way. For every action, the environment is going to give some reward to the agent. The reward may be positive, reward may be negative. Okay. If it is a negative reward, then in the next iteration, agent will take some different action. Okay. So what is our goal? Our goal is to choose some action in such a way that the total reward is maximized. Okay. How this total reward is computed? It is computed in this way: R0 plus gamma into R1 plus gamma square into R square R2 dot dot dot. Where is gamma? Gamma is called the discount factor. Okay, discount factor, and it lies between 0 to 1. Means if we are talking about R0, we are going to get full reward for R0. For R1, the R1 into some fraction. So some part of R1, some part of, and this gamma square mean more smaller fraction. So more smaller part of R2 in this way. So we have to sum up this reward. Okay. We are coming to the detailed formula of this. Okay. So this state transition diagram, this basically is followed based on a Markov decision process. Okay. It is a very simple rule, I will tell that. So what is there inside the reinforcement learning setup? There should be a set of states. Okay, finite set of state. If it is infinite, then the problem will be more difficult. So we assume that there is a finite set of states, and there is a set of action associated with the every state. Okay, in every state we can do some, perform some action. Okay, and at each state, at each discrete time, agent observes some state st belongs to it and choose some action at belongs to a. Okay, and then it receives an immediate reward called, let's say RT. Okay, RT is at time t the reward given by state st plus 1 to the agent. Okay, and every time we perform some action, our state gets change. Okay, it's come to st plus 1. Now what is Markovian process? Naturally, if we look at the some state st plus 1, it depends on the what action performed in st, and at st what action performed at st minus 1. Okay, in every previous state what action performed. For example, today I am here. Okay, I have performed some action. Let's say I have taken some education, some past action. So I have reached this state, and at this state I am doing some more work, some maybe more research. I will reach to next state. Okay. So what is Markov rule? Markov rule says that if we are talking about state st plus 1, we have to consider only the effect of current state st. Okay, whatever is there inside the current state, it include the all the past event. Okay, we don't need to compute all the past event, we have to only compute the current state. Okay, so Markov assumption is that we will only look at the previous state. Okay, previous state already is taken care of their previous steps. Okay, so this is the Markov assumption, and it is called Markov decision process. Okay. Reinforcement learning is on top of Markov decision process. So now come to the agent learning task. How a agent will learn. There are very simple. There are lot of equation. Actually, I have simplified the things as much possible, and you will. My objective is to make you ready to make some program or some small game using reinforcement learning. Okay. So what is the next thing? Next thing is agent learning task. So how agent will learn? Okay. So we have some definitions. First important definition is the policy. Okay. A policy is generally denoted with the notation pi, and it is a function from S to A. Every state it will take some action. Okay. And here is the reward function. Okay. RT plus gamma into RT plus 1 plus gamma square into RT plus 2 in this way. So what is RT? RT is any arbitrary point at Tth point, the reward function. Okay. And E is the estimate of the total reward. Okay. Our target is to learn some function pi, which is based on S2A. Okay. The agent transition. Now let's directly come to the most important part of reinforcement learning. We called value function. Okay. Value function is generally denoted by with every policy. With every policy pi, we associate a value function called v pi s. It is the notation. Okay. Pi may be any policy. Okay. And it is written as RT plus gamma into RT plus 1 plus gamma square into RT plus 2 in this way. So this summation is basically the value of v pi s function. Okay. Why we are doing this so many equation? Our objective is to create a recursion. Okay. And we will solve that recursion iteratively. That is our objective. Okay. That will be the training process. It will give us the optimal policy. It will solve all the game. It will solve the helicopter playing. It will solve everything. Okay. So we are just coming to that point. So for every policy v pi, we are going to get some equation like this. Okay. Where this RT plus 1, these are generated following some particular policy pi at some starting state s. Okay. And what is the optimal policy? Optimal policy is among all such value function, which one will give us the maximum reward. Okay. That is the optimal policy. So you know the argmax notation. Argmax of some function means we have to find out a point for which the function value is maximum, and that point we have to return. Okay. So for which pi we are going to get the maximum value of v pi s, that pi is called pi star. That is the optimal policy. So let's come to the some example to see this. Here is an example. It is called gammon game, but it you can visualize like any minesweeper type of game. Here is a board. Okay, 6-box board, and it is the initial state. Every position is 0 0 0 0 except the final state. This G is the goal state. Okay. So in every state there is 6 state. Let's say S1, S2, S3, S4 in this way up to S6, and we are at this bottom below step, which may be the starting point. So we have two options: we can move up or we can move left. Which option to follow? At the beginning, we don't have the policy value, we don't have the reward value. we know nothing. So all the values are 0, so we can choose any path. So from this left corner path we will move up, then right, and we will reach to the goal state. Okay, but now when we reach goal state we can get a reward. Okay. So let's assume that the reward for reaching goal state is 100. Okay. So if we are reaching goal state we are going to get the 100 reward. Now come to the policy function of my previous slide. How reward is computed? Reward is computed like RT plus gamma into RT plus 1 plus gamma square into RT plus 2 in this way. Let's assume that the gamma value is 0.9. Okay, I have shown you the gamma will lies between 0 to 1. Let's assume the value of gamma is 0.9 and come to this game again. So value of gamma is 0.9, so we are reaching to the goal state, we are getting the reward 100. Now in the next iteration, if we are reaching to a state where the reward point is 100, then we will then the reward of the previous value will become 91. Why? Because 100 into gamma 0.9 will give 90. Okay, so this will be 90. Okay, so here is an update. So if we move one more iteration we will get this value 90. If we move one more iteration we will get the value 81 for some other state, and we will get the value for 72 for some other state. This is after 6 iteration we will get this complete table of all the reward. So reward is computed in the backward process. Okay, so we need 6 iteration to complete this table. Now what is the policy? Let's say we are at the left bottom corner. Okay, so what will be the policy? We can move up, we can move right. If we move up, the reward we are going to get is 81. If we move right, reward we are going to get 81. Okay, so let's assume that we are moving at right. Okay, so now at this right box we have 3 options. We can move up. If we move up, the reward we are going to get is 90. If we move right, we are going to get the value 90, and if we are moving left, we are going to get the reward value 72. So if there is no policy, we can move anywhere, but a optimal policy will direct us that we have to move either in the direction of 90. Okay, either at top or in the right. Okay, so from the bottom left corner, if we move right, then top, we will reach the goal state. So it is a policy. Okay, and in fact it is a optimal policy. Okay, we have to learn this policy. How? Okay. So there is the optimal policy of this value function. The total value for all the state is given, so we have two optimal policy. Now come to that equation once again. Okay, so now for this is the one optimal policy. One optimal policy means inside this policy we can move to all the path. There may be other optimal policy. Okay, so optimal policy may be repeated. Now how to compute this thing? Okay, there is a famous algorithm called Q-learning algorithm. So for every reinforcement learning problem, we have to first identify the states. What are the states inside there? What are the action in every state? And then we have to design the value function and the policy function. Okay, so How we will write the policy function? We have seen that we need to compute the optimal policy. The policy is defined as pi star equal to, as I shown, the pi star is basically argmass of value function. But this value function can be represented in this format: the current state value, reward from the current state, plus the, let me show the equation once again. Okay, so it was the pi star equal to argmass v pi s, and what is this v pi s? V pi s basically the summation of all gamma I rt plus I. Okay, so if we exclude the only the last point rt plus 1, then we will get this equation: one last reward plus all the previous values. Okay, so pi star can be written in this way. Now we have to in Q learning algorithm, we have to we create a Q function which is defined in this way. This is the definition: Q of SA is defined as reward at the state SA plus gamma into V star delta SA, value, total value of the remaining state. Okay, so this is the definition of Q function. So for this value, what is the policy value? There are two values. One is policy, another one is value function. So we are basically make a recursion. So policy can be written as pi star s as argmax rsa plus b star this. Now if we replace this b star with the q, then we are going to get policy function s, optimal policy pi star s equal to argmass of qsa. Okay, we are still going to get a recursion. Now we will use this value into the previous function to get a recursion. How we can do that? We have b star s equal to max of qsa. Now we will write q stat. This is a particular state and a particular action. The value for this by definition of q, we can write this as r of stat plus gamma this, and this v function is basically can be replaced with the qsa. So qstat is basically r of reward of stat plus gamma into this. Now we got this recursion. Once we got this recursion, we can write a program. Okay, we can write a program with the initial value of reward. Let's say initial value of rewards are all 0 0 0 0, and the final value of the reward is 100. Okay, now if we run this recursion will update all the reward value from 100, then for previous state 90, then for previous state 81, then for previous state 72, and in this way this recursion will continue. How long it will continue? It will continue up to there is no more update in the q value. Once there is no more update in the q value, we say we have reached the optimal value of the reward function. Okay, now once we got the optimal value of the reward function, we can easily extract the optimal policy using this pi star s equal to argmax qsa. Okay, this equation will be used to compute the optimal policy. Okay, so that is what we are doing in this example. We have started with empty value, and here we can compute a q function for this game, and that q function will be recursively update, and it will update and get all this value. Once we got all this value, we will update the policy value. Okay, So we will get the optimal policy. Once we got the optimal policy, we will return this optimal policy to the agent. Now agent can play this game, okay, with any player, and agent will always win because agent has explored all the option. Maybe human is not exploring all the options. So here is Q learning algorithm. In the deterministic, you can easily implement this algorithm. So we have shown lot of equation, but we will when writing the program, we are not writing all those equation. Only thing we have to write a Q function, and we have to compute the pi star function. Okay, these two things we have to compute to get the optimal policy for the any game. Okay, so what is there in the Q learning algorithm? So first we have to for each state and action we have to we can create a table of this Q function, and that table can be filled from the previous iteration like the dynamic programming in the algorithm, and we will receive the reward every time, and we have to observe the new state every time. Okay, and the new state will be returned. That is the Q learning algorithm. We have the better version of the Q learning algorithm and its convergence. Okay, I have already discussed the convergence. Convergence means when there will be no more update. So here is a particular case. Let's say this is a particular state. Okay, and two steps are already done, 100, then this reward function r. Okay, now at this state, some next iteration, what the next iteration will do, if r move to right, then it will get the 100 value, and our the gamma function is, let's say the value of gamma is 0.9 in this equation in the bottom. If the value of gamma is 0.9, then what is the max between 63, 81 and 100? Max between 63, 81 and 100 is 100. So the reward function will get the 90 for the previous value. Okay, so in every box we will compute this Q value to get the reward value, and if we iterate this over every state, then we can optimize all these reward value. Okay, so this is the formula for updating the Q value in the Q learning algorithm. Here is some error function. Okay, inside the Q learning algorithm, we call the algorithm convergence when the optimal Q value is equal to this Q. Okay, so this is the definition of error. Okay, this Q hat is the value of Q at some arbitrary position, and this QSA is the optimal Q value, and the difference between them is the error. We can also uh, put some criteria on the error for if the in some particular game, if it is not converging, then we can put some criteria on the error. If the error value is less than 0.5, then we can terminate it forcefully in this way. I will show you in the real program how we do that things. Okay, so this is the optimal Q value, and so let's see the program once again, and here is the TD learning. I will discuss it again. Okay, so uh, that is the program. uh, So it is a very simple program. I am using just NumPy and the pickle, and you can choose any other instance. Pickle is basically for creating serializing the data point. Okay, there is some class for state. Okay. As we need to create handle all the state, so there is some class for state. What are the different state in the tic-tac-toe? There are the winner state and the and we are using some hash value, okay, inside this state class. And this is for creating the board. Okay. I'll share this program with you. So this is the board size, and for creating the board, and we have to actually write the function for how to move into the next state, okay, and how to print the board value. And this is for printing the board value star and x inside the board value. And this is for showing all the state, okay. Now this is for player. What are the player? Two player. Player one is the human player, and the player two is the agent. Okay. So we have to train the agent. So here is our training function for that. Let's directly come to the training function. Okay, initially we initiate the populate the value of the policy with random, and then we update the value of the uh, lambda. So let's come to the training phase. Okay. So it is the winning condition, and this value of the epsilon. This is the error rate. I can make it 0. Okay. If we make it 0, then the player will uh, let's say player 2 is the agent. If we make it 0, then it will train more and it will be more efficient. Okay, there will be no error in the agent. So I am showing you the last level, this training state. Okay, so how much I am training? I am training 1e5. 1e5 means uh, 1 into exponent of 5. So it is basically 10 to the power 5. Okay, so 50. Okay, if I reduce this training for, let's say, uh, I am taking is 2, and for this complete I am taking the value is 1. So I am making very minimum training to the agent. Okay, let's run this program again. Okay, so the program is running. Now we can see for player 1 there is some win rate, and player 2 there is some win rate. So initially the win rate for player 1 is very low, and the win rate for player 2 is player 2 is very low, and player 1 is very high. And it is as there is more iteration, this win rate is changing. Okay, win rate is changing for human player, and the agent player the win rate is increasing. Okay. Oh, I have not saved this, so let's terminate this program. Let's save and let's run it. Okay, so as I am reduce the training part, so there is very little training and we just got the board. Now if I play with this agent, I can easily beat this agent. Okay, so I have given the middle, choose the middle box, and agent has chose this. So now I am choosing, let's say, E. So agent is choosing this. So now I am choosing uh, say Q. So agent has left the game for me. Okay, so I have the winning condition. If I put W, so I won. Okay, because I have made less training, so the policy value of the agent is not optimal. So agent is losing. But if I make more training, then I cannot win the game. Okay, and you can write the program for this. Only thing you have to write is the q learning algorithm. You have to implement the q learning algorithm for say a particular problem. Okay, so I have stopped the sharing. So now you can ask the question and I can explain something more. Any question for your
Dear
side?
participants, if you have any question, please ask. Sir, I guess there is no question from the participant side. You may continue, sir.
Okay, so what is there in summary in reinforcement learning? Reinforcement learning is very good thing. Okay, so it's about in for we take some example of that tic-tac-toe. Some particular condition of the tic-tac-toe. Let's say there are uh, last bit. Okay, last position to fill. There is one winning condition and there are two more position empty. So agent can choose any one of these three. Agent can win or agent can choose the other option. So if agent is choosing the winning option, agent is going to get the good reward, maybe the 100 for the winning case. And if it is not choosing the winning state, then that action will be rewarded with the less value. Okay, and this learning does not, unlike machine learning algorithm, this reinforcement learning does not need a lot of data, lot of past data. Okay, it is generated directly from the problem. Okay, and what we need to know only the last state, last winning condition. Okay, and we can write a Q learning algorithm. We have to design a Q function for that particular problem, and you can design it for any problem. And most interestingly, if you are doing some research in algorithmic field like traveling salesman problem or some network problem, for example, uh, uh, the that traveling salesman problem, that is NP hard. Okay, if we train a reinforcement learning agent to find out the traveling salesman path, okay, then it will become a trend model. After the training will takes a lot of time, but once this reinforcement learning model is trained, it can solve the traveling salesman path in constant time. given a graph, it will just visit the graph and return the optimal traveling path. And we have some more beautiful research problem like delivery optimization problem. Okay, delivery optimization problem is like we are having inside a big city the delivery people. For example, let's take Amazon delivery service. Okay, so those guys are moving from one house to another house and they have some path. Okay, and they have some weight carrying inside their bag. Okay, so the objective will be they want to free the heavy weight early as well as complete the whole path and return to their office. It is little bit different than the traveling salesman problem. He has to uh, uh, empty his bag. Okay, so that can be solved easily using reinforcement learning. Previously we used to solve this in algorithmic method. We are used to design some algorithm to solve this, but now we can design some reinforcement learning agent and it can return as the optimal delivery path. Okay, in constant time. That is not NP hard. Training is difficult, it take lot of time, but once the optimal policy is learned, it can return the solution in constant time. Okay, there is many more problem, real life problem, where we can directly apply reinforcement learning and you can go for good research. The previously many network problem or like algorithmic problem or any other real life problem, graph theoretic problem, that can be easily solved using trained reinforcement learning algorithm. And it can allow you, if you allow some error, then you can train it more quickly. If you have more time, then if you make rigorous training, then it will exactly give you uh, the optimal path. Okay, so that is a many more beautiful research area using reinforcement learning. You can try it. So that's all for my presentation. If you have any question or any query, you can ask.
There is no previous data is required here. Am I audible?
Yes, yes.
Is there no record any previous data?
No, no, no.
Like
There is
learning?
no data. No data is required, and it is unlike machine learning algorithm. We don't require any data. For example, that game I have shown, for the last value winning state, we are giving the reward, and in fact, we are not giving the reward manually. For winning state, it is iteratively pre-computing the reward for the previous state. For tic-tac-toe example, for the last option,
So the application area of the machine learning and the recursive are totally different.
yes, yes, it is totally different. It is if any real life problem,
Not like
uh, for
not
any
like
real
the
life problem,
machine learning and then deep learning will come.
you
So
can, yes, yes,
and actually we learn first the machine learning, then the same problem will be applied for the deep learning purpose. But the same problem is not applied by reinforcement learning. It is automated system.
yes, it is automatic, and we can that training part we can mix with the representation learning. Deep learning is basically representation learning, and reinforcement learning is basically used for control and planning. Okay, so if we that training part we replace with the deep learning representation learning framework, then we call it deep reinforcement learning. And basically I have shown you that game, that AlphaGo. That AlphaGo is the creation of DeepMind lab inside the Google. Okay, they use deep learning algorithm. Okay. And there is a very beautiful lecture slide by David Silver. David Silver is the most genius scientist of deep mind lab. Okay, and we can basically combine the learning with the reinforcement learning, but only for the training purpose, so that we can make a rigorous training inside the reinforcement learning for the problem like chess and that go. Uh, they are very complex problem, so we need rigorous training, and deep learning make that rigorous training faster using the
My last question, how to learn the machine or how to learn the agent? Actually, the agent can learn from the human's position or human's
no no no
option.
no 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 no
So how to learn?
agent will
Is it
learn only from the reward. Okay, and
reward
reward
means they arbitrarily choose any position first.
no
Then we learn another.
initially arbitrary, but the last position
Last position is the.
where the agent is reaching the goal state, that will be rewarded.
So they are
And
not following the humans steps.
Initially agent will move arbitrarily. Okay,
Arbitrarily, not follow
as
the human steps.
as I shown in that automatic or autonomous helicopter example, the helicopter is moving arbitrarily
Moving arbitrarily.
initially, but if you complete that audio or video from up to the last step, after 5 or 10 minute, the helicopter is moving smoothly. It is not moving arbitrarily, so it is already trained. Okay, so if we move
Thank you very much.
start with a self-drive car, then initially the self-drive car will go anywhere. We have to make sure that we have to put some sensor that it will not hit anything, any object. That we have to ensure. Okay, using some sensor, and then we will leave that self-drive car to move arbitrarily. It will move arbitrarily, and it will get some reward. Okay, for example, in the state road it is arbitrarily moving the steering in the left direction, so it will get some negative reward. Okay, once it's got some negative reward, it will not repeat that path again. Okay, just like small child, what they do, uh, they are sitting in the bed, so they will go to the corner of the bed, and they will fall down from the bed. Once they fall down, they
Yeah.
will never repeat that step again. They will in the next step they will uh, go to corner but not jump. Okay, and after few more training, they will even avoid to go to the corner of the bed, because they will learn that there is some risk. Okay, so in this way agent will learn. So it is basically the how the human brain or all the animal brain trained, the same policy is follows inside the reinforcement learning. So it is a dangerous thing. It can create a more vulnerable efficient machine than a human. Okay,
Right, right.
in the near future.
Thank you very much.
Okay, so thank you from my side. Thank you for listening.
Dear participants, do you have any queries? If you have any queries, please ask. Sir, I guess there is no further query from the participant side. I would like to express my gratitude for accepting our invitation and deliver the lecture, a
It is
wonderful
my
lecture
honor.
for us.
It is my honor.
Thank you, sir.
Okay, anytime you can connect me if you want to learn more about that. I have some YouTube channel also in the name of Algorithm for All. There I am planning to put many good reinforcement learning video and lecture. You can follow that thing.
Sir, can you please put your email ID in the chat box?
It is Saha.Suman. Yes. I have given my Gmail ID and my YouTube channel link. Here I put many good, beautiful videos for on algorithm, cryptography, and reinforcement learning. Okay.
Thank you, sir. I think from your today's speech and from the channel, the participant will be entirely benefited. And thank you again for giving us your precious time.
Thank you
Thank
for
you, sir.
inviting me. Okay. Thank you.
And dear participants, I will be putting the attendance link in the WhatsApp group within 5 to 10 minutes. Please mark your attendance. Thank you all. This is all for today. And tomorrow we will be starting our program by 11 a.m. Thank you.